Okay, welcome back. We have discussed wave equation and its different cases for solving the wave equation. That is initial condition like displacement is given and velocity 0. In other case, velocity given, displacement 0, and both velocity and displacement are given. We have solved all these kind of equations, cases for wave equation. Now we will discuss D'Alembert solution for wave equation. It is also spelled as D'Alembert solution for wave equation. So we have our one-dimensional wave equation dou square y by dou t square is equal to c square into dou square y by dou x square. For solving this wave equation by using this method, we first of all take u and v as function of y. Okay, that is u and v. Y is function of u and v, where u is equal to some function of x and t. So we take here u equal to x plus ct, u equal to x plus ct, and v equal to x minus ct. So then now the situation is y is function of u and v, and u is function of x and t. Okay, x and v is also function of x and t. Actually y was function of x and t because then only we'll get a term like this, but we take some more detailed view to solve this or derive this solution for D'Alembert solution for wave equation. We take u equal to x plus ct and v equal to x minus ct, and u and v are just variables, or y is a function of u and v. So you can think about this picture. This is a tree for finding partial derivatives. Okay, so now we are expected to find partial derivative with respect to x, dou y by dou x. So using this tree you can clearly find the partial derivative with respect to x. To reach x we have to travel via u and we can reach x. Also we can travel via v and we can reach x. Okay, so dou y by dou x we can write as dou y by dou u into dou u by dou x plus dou y by dou v into dou v by dou x. But we also have, we can take this as equation number 1. We also have from equation number 1 u equal to x plus ct and v equal to x minus ct. So we can find dou u by dou x, which is equal to 1. Okay, dou u by dou t is equal to c, dou v by dou x is equal to 1, dou v by dou t is equal to minus c. So we can see all these things. Okay, we can substitute all this in the equation. What we get is equal to dou y by dou u into dou u by dou x is 1 plus dou y by dou v into dou v by dou x is again 1. So what we get is dou y by dou x is equal to dou y by dou u plus dou y by dou v. So you can also write this only in terms of the derivative things. That is, you can also write this that dou by dou x is equal to dou by dou u plus dou by dou v. So how, when you take whole kind of y, you will get the same thing as we get here. Okay, so we use these two for solving or finding the first stage. So we keep it as equation number 2 and we keep this as equation number 3. Okay, now actually our wave equation is dou square y by dou t square is equal to dou square c square into dou square y by dou x square. So actually what we need is dou square y by dou x square. Okay, so we find dou square y by dou x square, which is equal to dou by dou x of dou y by dou x. Okay, so here instead of dou by dou x we substitute this. Okay, instead of dou by dou y by dou x we substitute this. So from equation number 2 and 3 we go further forward to find the dou square y by dou x square. So this is equal to, instead of dou by dou x we put dou by dou u into plus dou by dou u plus dou by dou v. Actually this is not multiplication, it's taken off. Okay, so dou by dou y by dou u plus dou y by dou v. So now we take this inside. Okay, this operators inside. So we component wise we take this inside. So what we get is, this is equal to dou square y by dou u square plus dou square y by dou u dou v plus dou square y by dou v dou u plus dou square y by dou v square. Actually this is equal to dou square y by dou u square plus 2 dou square y by dou u dou v plus dou square y by dou v square. Okay, we can keep this as equation number 4. Okay, so this is what dou square y by dou x square. Similarly we will find dou square y by dou t square. Okay, we have to find dou square y by dou t square. For that, first of all we need to find dou y by dou t. Okay, we have to find dou y by dou t, and you remember the assumption we take, that is u equal to x plus ct and v equal to x minus ct, and y is function of u and v, and u is again function of x and t, and v is again function of x and t. Okay, by taking in this mind we also get dou u by dou t is equal to c, and dou v by dou t is equal to minus c. So we can keep all this in mind. So now we take dou y by dou t. So to take that, we can travel from y via u to t, and we can travel from y via v to t. Okay, so these two parts we have to take. So dou y by dou t becomes dou y by dou u into dou u by dou t plus dou y by dou v into dou v by dou t. Okay, but we can substitute these two. Okay, dou u by dou t is equal to c, and dou v by dou t is equal to minus c. So we can substitute this. So what we get is dou y by dou u into, instead of dou u by dou t you can put c, plus dou y by dou v into, instead of dou u by dou t we can put minus c. Okay, so what we get is, we can take c outside. Okay, c into dou y by dou u minus dou y by dou v. So this is actually dou y by dou t. We can keep this equation number 5. Okay, also like what we did in the previous case, in terms of operator also we can write dou by dou t is equal to c into dou by dou u minus dou by dou v. Okay, while taking off y you will get the same thing as equation number 5 has. So you can keep this equation number 6. Okay, now what we need to do is, we have to find dou square y by dou t square is equal to dou by dou t of dou y by dou t. Okay, so for this we substitute 5 and 6. Okay, first of all we put 6 instead of dou by dou t, that is c into dou by dou u minus dou by dou v into, instead of dou y by dou t we substitute 5, c into dou y by dou u minus dou y by dou v. Okay, so we can take c, both c outside, we can take c square. Now you can take component wise derivative, that is dou u dou dou by dou u of dou y by dou u, that is dou square y by dou u square minus dou square y by dou u dou v minus dou square y by dou v dou u plus dou square y by dou v square. So taking all this we get c square into dou square y by dou u square minus 2 dou square y by dou u dou v plus dou square y by dou v square. Okay, so we keep this equation number 6. 7 we can keep this as equation number 7. Okay, also we have the one dimensional wave equation dou square y by dou t square is equal to c square into dou square y by dou x square. We already have this term, and from the recent equation number 7 we have this term. So we have look at the dou square y by dou x square term. This was dou square y by dou x square we have received in the previous step. Okay, so using equation number 4 and equation number 7, okay, equation number 4 and equation number 7 we can equate, that is this is dou square y by dou t square. So c square into dou square y by dou u square minus 2 dou square y by dou u dou v plus dou square y by dou v square is equal to c square is in the wave equation. In the wave equation c square we substitute that, and then you substitute equation number 4, that is dou square y by dou x square, that is equal to dou square y by dou u square plus 2 dou square y by dou u dou v plus dou square y by dou v square. From this you can cancel c square. Okay, and taking this equation in one side we get, okay, now we take this term one side, what we get is 4 dou square y by dou u dou v equal to 0, or this implies dou square y by dou u dou v equal to 0. Okay, so we have dou square y by dou u dou v equal to 0, but we have to solve this particular equation to get the solution. So we can keep this equation number 8. So we have learned that if a particular partial differential equation contains only one term, one derivative term, it is better to use the method of direct integration. So you can solve this particular thing by using method of direct integration. Okay, so for that we can take integrate with respect to this function with respect to y. Okay, first of all we can integrate this function, equation number 8, integrating with respect to v. What we get is, okay, so we have first of all we integrate with respect to y. Okay, so we get dou y by dou u is equal to, so we are integrating with respect to v, so we have to take some function of u, so h of u. Okay, now we go further forward, now we integrate again with respect to u, so now integrate this again with respect to u, we get So now we get y is equal to integral, actually this is y is equal to integral h of u into, so since we are integrating with respect to u, we can write du. Okay, so by integrating this, what we get is, so we can write this as h of u, integral h of u, we can write capital H of u. Okay, we still keep this as a variable, and then plus, since we are integrating with respect to u, we can keep that as a some function of v, so we write g of v. Okay, so y is equal to h of u plus g of v, we write like that. Now for getting the solution, so now here we can substitute, instead of u and v, you can substitute as we take in the case, we have taken that u equal to x plus ct and v equal to u equal to x plus ct and v equal to x minus ct. So we can substitute that. So what we get is y equal to h of x plus ct plus g of x minus ct. So this is the general solution of wave equation by using this method. So this doesn't end here, we have to find h of more precise solution by applying the conditions, initial conditions, like initial displacement and initial velocity. So after that we will get more precise or more clear solution for the wave equation. So this can be taken as the general solution for one-dimensional wave equation by using D'Alembert's method. Now we'll determine capital H and small g. Okay, this is actually small g. Okay, so to determine that, first of all, let us take some initial condition, that is y of x0. Initial displacement is f of x and initial velocity dou by dou t of y of x0 equal to 0. So suppose these are two initial conditions, so we apply this in the general solution and try to solve for h and g here. Okay, so now first of all we actually differentiate partially with respect to t. Actually this y is actually y of x and t. Okay, is equal to h of x plus ct plus g of x minus ct. Now we differentiate this partially with respect to t. What we get is dou by dou t of y of xt is equal to, so we have c into, okay, since we are differentiating with respect to t, is equal to c into capital H dash of x plus ct plus, actually we will get minus c there, so we can take minus c into g dash of x minus ct. Okay, this thing. Now applying the first initial condition, that is this thing we can apply, since it is given as 0, we can apply that. So dou by dou t of y of x0, we apply this, that is we take t equal to 0 in the equation, so we get this is equal to, when t equal to 0, c into h dash x minus c into g dash x. Okay, c into h dash x minus c into g dash x. This is equal to 0, since the initial velocity is given as 0, this is equal to 0. That implies again c into h dash x is equal to c into g dash x. Okay, c into g dash x, small x. Okay, so in this we can cancel c from both sides, so what we get is h dash x is equal to g dash x. So cancelling c in both sides, h dash x is equal to g dash x. Okay, so now we can integrate with respect to x to get more clear values for h, that is h of x is equal to g of x. So that doesn't end there, we have to put some constant c also, okay, plus c. Now we will apply the second initial condition on this particular equation. Okay, we'll use this equation and apply the second initial condition, y of x0 equal to f of x on y of xt equal to h of x plus ct plus g of x minus ct. Okay, so what we get is f of x is equal to y of x0 is equal to h of x plus g of x. Okay, we get this. That means we can substitute, instead of h of x we can substitute g of x plus c. Okay, we can substitute g of x plus c, that is we have already received that h of x is equal to g of x plus c. So we can say that f of x is equal to g of x plus c plus g of x. Okay, g of x plus c plus g of x. So we can take this one side. So what we get is 2g of x plus c is equal to f of x. F of x is equal to 2g of x plus c. F of x is equal to 2g of x plus c, and 2g of x is equal to f of x minus c. Or g of x is equal to 1 by 2 into f of x minus c. So now we have received g of x. Okay, so similarly we have to find capital H of x. That is very easy. We already have h of x is equal to g of x plus c, so we can use that. So h of x, since we have h of x is equal to g of c, so this, in this particular equation we get h of x is equal to, actually g of x is 1 by 2 into f of x minus c, okay, plus c. We can distribute this 1 by 2 into f of x minus 1 by 2 into c plus c. Okay, what we get is 1 by 2 into f of x plus 1 by 2 c. Okay, we can take this 1 by 2 outside, so it's equal to 1 by 2 into f of x plus c. Okay, so we have received h of x and g of x, right? Here h of x and here g of x. So we can write once again here, we have h of x is equal to 1 by 2 into f of x plus c, and g of x is equal to 1 by 2 into f of x minus c. Okay, now we can go further forward, but we have defined as y of xt is equal to h of x plus ct plus g of x minus ct. Okay, so we have got h of x is equal to this and g of x is equal to that, and now we have to find h of x plus ct. We just need to substitute, instead of x we need to substitute x plus ct, that is equal to 1 by 2 into f of x plus ct plus c, and g of x minus ct is equal to 1 by 2 into f of x minus ct minus c. Okay, so since we have y of xt is equal to h of x plus ct plus g of x minus ct, we can substitute these two in this equation. So finally we get y of xt is equal to 1 by 2 into f of x plus ct plus c plus 1 by 2 into f of x minus ct minus c. Okay, now we can cancel this 1 by 2c. Okay, we can cancel this 1 by 2c from here. It is 1 by 2c, here it is 1 by 2 minus c. So finally what we get is equal to 1 by 2 into f of x plus ct. Okay, we can take 1 by 2 common plus f of x minus ct. So this is y of xt. Okay, so where f is the initial displacement. Okay, so now we received the solution of one-dimensional wave equation by using D'Alembert's method for the initial condition f of x. So we can use this particular method to solve the initial value problem, which initial displacement is given. So we just need to substitute this initial displacement and find the answer. This is very simple method than compared to the method of separation of variable method and solution method. Now let us have a look at one problem. Find deflection of vibrating string of unit length having fixed end with initial velocity 0 and initial deflection f of x is equal to k into sine x minus sine 2x. In this clearly we have to find the vibration of string which is attached at both ends, and it is allowed to vibrate with the initial deflection. So initial deflection is given, that is y of x0, that is equal to f of x equal to k into sine x minus sine 2x, which is given, and initial velocity is 0. Straight away initial velocity was given as 0. So here we can use D'Alembert's solution for this particular wave equation, that is y of xt is equal to 1 by 2 into y of xt is equal to 1 by 2 into f of x plus ct plus f of x minus ct. So straight away we can substitute this in the equation. Okay, that is we just need to replace this x with x plus ct, and wherever you find x with x plus ct first and then x minus ct. For this we represent with x plus ct, and this we represent with x minus ct. That is 1 by 2 into, we have to take k into sine x plus ct minus sine 2 into x plus ct, okay, plus k into, now you apply x minus ct, k into sine x minus ct minus sine 2 into x minus ct. Okay, now we have to simplify and solve to find y of xt. Okay, now we have to simplify this. Here first of all we can take k outside, so k by 2 into, and take the term sine x plus ct and sine x minus ct together. So sine x plus ct plus sine x minus ct, okay, minus, I can take minus outside, sine 2 times x plus ct plus sine 2 times x minus ct. Okay, so now we can use the formula sine a plus b plus sine a minus b equal to 2 sine a cos b. We can apply that. sine a plus b plus sine a minus b is equal to 2 sine a cos b. We can apply this in both these terms. Okay, so which gives k by 2 into so sine x plus ct. So we can take this as a, this as b. So a plus b plus sine a minus b. Okay, so 2 sine x sine a cos ct. Okay, minus the other term becomes 2 sine 2x 2 sine. Here you can take 2x plus 2ct, 2x minus 2ct. So this is a, this is b. Okay, a plus b, a minus b. 2 sine 2x cos 2ct. Okay, so this is actually our y of xt. So we can check whether this satisfies the conditions, initial conditions. For that, first of all, we substitute uh, y of x0 and we have to get k into sin x minus sin 2x. We will try that. Okay, that is, we have to get y of x0 is equal to k into sin x minus sin 2x. So we try this in this. Okay, so in this y of x0 is equal to k by 2 into, wherever you find t you put 0, 2 sine into cos 0 1 minus 2 sine x into cos 0 1 and sine 2x into cos 0 1. So when you take this k by 2 into 2 sin x minus 2 sine 2x, which is k into sin x minus sine 2x, that is, it clearly is, it's equal to f of x, the given question. So it satisfies the condition, so we say that this is right. Also we can check whether it satisfies initial velocity equal to 0, that is dou by dou t of y of xt we have to find first. Okay, dou by dou t of y of xt we have to find first. So in that we can put k by 2 into, wherever you find t you have to take derivative, 2c into sin x derivative of cos minus sin ct now we will find derivative. Okay, so y of xt is equal to, okay, y of xt is equal to k by 2 into 2 sin x into c into derivative of sin minus cos minus sin ct minus 2 into sin 2x into 2c into derivative of cos minus sin 2ct. Okay, now you apply t equal to 0, what you get is dou by dou t of y of x0, that is initial velocity. So when you apply 0, sine term becomes 0 and this clearly is equal to 0. So it satisfies both these initial conditions. So we can say that this particular function or y of xt is equal to this particular function is solution of that wave equation for the initial conditions given. Okay, now let us look at another problem. Find deflection of vibrating string of unit length with fixed endpoints with initial velocity 0 and initial deflection as sine square pi x. So here also initial velocity is given at 0 because we derived solution for initial velocity 0 and deflection with function. So usually that is there in the syllabus. Okay, so we have y of xt is equal to 1 by 2 into f of x plus ct plus f of x minus ct. Okay, so we apply this in this particular uh, particular problem. Okay, so for that what we do is we first of all substitute all these values in this particular formula. Okay, so we in place of x we have to take x plus ct. That is what we get is equal to 1 by 2 into, instead of that, a sine square pi into x plus ct, okay, plus a sine square pi into x minus ct. Okay, now we what we do is we take a which is common, or take a outside, is equal to a by 2 into a, take a outside, sine square pi into x plus ct plus sine square pi into x minus ct. Okay, now for sine square theta we substitute, we have sine square theta is equal to 1 minus cos 2 theta divided by 2. Okay, we substitute this instead of sine square pi x plus ct. So what we get is a by 2 into, instead of sine, 1 minus cos 2 pi, 1 minus cos 2 pi x plus ct divided by 2 plus 1 minus cos 2 pi x minus ct divided by 2. Okay, now we will simplify this. We take 4 which is common, we take that outside, so this is equal to a by 4 into 1 minus cos 2 pi into x plus ct, okay, plus 1 minus cos 2 pi into x minus ct. Now we can go one more step forward. We can take that 1 which are common, we can take that together. So we take, this is equal to a by 4 into 2 minus, okay, we have two terms, cos 2 pi into x minus ct, okay, plus cos 2 pi into, sorry, x plus ct and x minus ct. Okay, now we take a 2 pi 2 cos a plus b cos a minus b form. Okay, this is, I can write more clearly. So this is equal to a by 4 into 2 minus, this is 2 pi x plus 2 pi ct, this is 2 pi x minus 2 pi ct. So a plus b, a minus b. So what we get is cos a plus b plus cos a minus b. So 2 cos a cos b. Okay, 2 cos a is 2 pi x cos 2 cos a cos b. Okay, 2 cos 2 pi ct. Fine. So we can go further, I mean, we can take even 2 common, which is which can be brought outside, is equal to 2a by 4 into 1 minus cos 2 pi x cos 2 pi ct. Okay, we can take this, we can cancel, so this is equal to a by 2 into 1 minus cos 2 pi x cos 2 pi ct. Okay, so this is the solution. You can also check whether it satisfies the initial condition by substituting t equal to 0. For example, okay, we can substitute this y of xt. Okay, now we can substitute y of x0 equal to a by 2 into 1 minus cos 2 pi x into 1. That is a into 1 minus cos 2 pi x divided by 2. So 1 minus cos 2 theta divided by 2 is equal to a into sine square pi x, which was the question. Now we can also check whether it satisfies initial velocity dou by dou t of y of xt, and we can find dou by dou t of y of x0 equal to 0. You please try yourself, you will get it. Okay, so this is all about D'Alembert's solution for one-dimensional wave equation. So next is heat equation. So we'll move to next section, heat equation, one-dimensional heat equation.